Welcome today on behalf of the Embassy of Poland in London and Association of Polish Engineers in Great Britain on one of our two webinars organized as a part of the British Science Week. Today's webinar is given by Dr. Gary Barker and it's titled The Coronavirus Data Deluge, Coping with Complexity, Confounding and Causality. Before we go to the webinar itself, there's a couple of things I wanted to start with. The first one is a little bit about the housekeeping for today. First of all, I think you should be muted, so just to avoid any disruption during the webinar. The webinar is also recorded, so if you don't wish your image to be displayed, please switch off your camera. We would like to make the session as interactive as possible. So if you would like to introduce yourself a little bit in a chat, say your name and where you're connecting from, which part of the UK or Europe, or maybe which part of the world you're connecting today, it would be very, very nice. Please also use chat to pose the questions. I will be collecting the questions and there will be a Q&A session in the end. And either we're gonna read them or there will be also opportunity to ask the question directly. I'm sure you have many questions. You can ask as many questions as you want and as controversial as you wish. I'm sure Gary will respond to you, maybe not, if not during the webinar, I'm sure he'll be happy to do that offline. My name is Ewelina Wachnicka. I am the host of today's evening on behalf of the Polish Engineers Association and Polish Embassy in London. Before we go into the actual part of the webinar, I would like to give you a little bit background of the association and why we are actually organizing this evening tonight, this webinar tonight. So the Association of Polish Engineers in Great Britain is one of the oldest professional associations outside of Poland. And just a little bit of history. The association, the first meeting of the general meeting of the association was on the 7th of December of 1940. For those of you who know history well, you know that this is the first night of 57 nights when the Nazi started bombarding London. So it's quite a very historic moment for the association as well. We are a charity organization, and through the 8 years of our activities, maybe the scope of the activities has been changing a little bit, but the nitty-gritty, the whole core of our existence of the association is basically bringing together engineers and professionals working and living in the UK. And what we do, mainly we are focusing on organizing training and courses and workshops, seminars and conferences. Conferences and webinars we organize regularly on a regular basis, at least once a month. On top of that, we've got a very well-developed mentoring program and coaching, supporting members of our association, and especially helping those who are just moving to the UK, who gain their education in Poland, and they may move to the UK market, and they don't really know how to maybe start their professional life. So we are there to help them. We are also creating the space for exchange for ideas and experiences. We share our route from how we became the expert and the professionals working in the UK. How did we actually landed where we are with our job careers? We also support the integration of Polish communities into the British society. We collaborate with engineering organizations in the United Kingdom, Poland, and other countries. The big part of our activities is also networking. It's opportunity to meet each other, also on a professional side, but also on a personal side. So we do organize lots of events on that side, in that respect. The very important aspect is that the Association of Polish Engineers is a professional affiliate in Engineering Council. The affiliation recognizes the contribution that our organization makes in the field of our expertise, which is engineering. So as I said, over the years, maybe the activities has changed a little bit. They're evolved. We extended some of our scope, and that's why this brings us to today's webinar. Over the last 5 years, we've been actively involved into promoting science. And within that space, we've got 2 different activities. The first one is regular visits in Polish Saturday school. So for those of you who are not familiar, many Polish families who are settled down in the UK, they send kids on top of the British daily school, they send their kids to Saturday school, which focuses on teaching the language, Polish language, literature and history, Polish history. And our activity, our aim is to visit as many schools as possible and organize science workshops, lectures. And so far we visited 6 schools. We try to organize at least 2 schools a year. And we reached out around 1,500 students so far. And the workshops are organized by the volunteers of our organizations. So these are people who are either professionals working in a companies in the UK, or they own companies, or they also work in the science institutes or government agencies. So the range of the volunteers and their professional, their skills, their expertise, it's actually very broad here. So the workshops that we organize are either science, from art to science, basically. So it all depends from the volunteers who are part of the project. Other activity is the Science Day. Science Day, we collaborate with 3 different professional organizations in London. So we organize the Science Day every 2 years. So far we had 2 editions in 2017, 2019, and we should be actually today or within the next 10 days, which are part of the British Science Week, we should have had our 3rd edition. Unfortunately, that didn't happen. Hence today our webinar. The Science Day, I think, brought around 1,000 visitors over these 2 editions, and we organize lectures, workshops, interactive workshops, and also the science show, where the kids and also adults in different age and different backgrounds can join to any sessions, can sign up for free to any of the webinars or the activities. The activities are mainly organized by the Polish professionals working in the UK in different parts of science, technology, and engineering and mathematics. So this is across the different parts of the STEM. So coming back to today's webinar, I'm really pleased to welcome Dr. Gary Barker. And I said a lot of word Polish here, but Gary has a big connection with Poland. First of all, Gary was my PhD supervisor here in the UK, in Norwich. I know Gary for over 11 years, not only as my supervisor for 3.5 years, but most of all as my friend, a very good friend, and actually the person who really believed in me from the very beginning, and I think who had one of the biggest impact on my professional career, and that would be something that I'm really grateful to Gary. I posted here Gary's biography, but I'm not going to read it, and I would like to take an opportunity to present Gary with my own words, how I Gary know, and through the expertise that Gary has passed on to me as well. So the topic today's webinar, there was a couple of ideas what we can present today, but in the light of the ongoing pandemic, which unfortunately affected all of us, our daily life, probably today, never before we have been so exposed to data as we are today, to see every day graphs, charts, that we don't really know maybe what they mean. We see them colored red and we are petrified. So what does it mean? How can we interpret this? How can we not to feel lost? And there was a suggestion, maybe we can do a webinar in tackling, helping to understand this, the data, the amount of data that we are really exposed to over the last year. And when I was thinking about the speaker, I could not think of a better person than Gary, because Gary has dedicated his life to data, to numbers, to equations. And by background, he's a physicist, but I think he's one of the very few scientists who, first of all, can bring together many disciplines of science. So, as I said, physics, mathematics, statistics, but also social science. Gary is without doubt, I can say he's a world recognized expert in food science, in risk assessment, in mathematical modeling. And he's the one who really very well makes the link between data and how does it translate to the policy making, and therefore how does it translate into our daily life. Gary has been working a lot with different institutions, government bodies, which I'm not going to name, but what I can tell that many of the regulations that probably are implemented today by the European Union, I'm sure Gary has contributed to it. Personally, I know Gary is a big fan of art, painting. And if you have a Polish PhD student, you know that sooner or later you'll be exposed to Polish national food or even drink. And I know over time Gary became a fan of Polish vodka. So without further ado, as I hope, Gary, you don't mind introducing you with a little bit of personal note. I'll be very happy and I'm looking forward to your lecture. So over to you, Gary.
Can everybody hear me? Hopefully,
yes.
Hopefully my screen should come up soon. How is that? Can you see that?
Yes, so good.
Okay, good. Well, I think we're ready to go.
Brilliant.
Excellent. Well, thanks for the introduction. I'm not sure I'm half of the things that you claim I am, although I can't deny the vodka. I'm going to talk about coronavirus. It says coronavirus in the title, so I need to give some disclaimers first. I mean, I'm not a clinician at all, and so whatever you do, don't take anything that I say as directly relatable to your own health. Go and seek a professional. I'm not an epidemiologist either, so I'm going to talk about some epidemiology, and really you should talk to a proper epidemiologist about that. I'm going to try and avoid any real data sources. I'm certainly not going to favor any data sources in this talk, so it would be unfair to do that. So I shall try and be generic in terms of talking about data. The other thing I would say is that I'm not going to talk about any details really either. I'm going to avoid details. I don't think it comes across well in a webinar to do details. And I think only one of my slides has got any mathematics on it. I'll give you a warning for those people who are nervous about mathematics when that comes up. So that should be okay. And the other thing I need to warn everybody about is that I'm sitting at home, connecting through my home wireless internet, which can be flaky. So if it does go down for a while, sit tight. Takes about 30 seconds usually to come back, and we'll stick with it. Okay, so let's go on. So I'm going to start with this quote. The 21st century will be the century of complexity. Actually, that's a quote from Stephen Hawking. He said that in about 1999. He was actually being interviewed by a radio program and a magazine. And I think they were trying to wind him up, actually. I mean, anyone who's ever met Stephen Hawking will know that he was the sort of person you shouldn't try and wind up. But I think they were trying to get him to say that biology was going to overtake physics and that physics was a redundant science. And he was never going to say that. And he came up with this phrase, the 21st century will be the century of complexity. And he never really explained what he meant. But I think it turned out that he was quite accurate. A lot of the systems that we look at in science now are what are termed complex systems. That goes from climate change and financial markets to all kinds of things to do with social interactions and social media. Those things are looked at from the perspective of complex systems. In actual fact, around about that time, I was working on a complex system called a sand pile. And a sand pile is often used as a kind of a laboratory for complex systems analysis. And I was actually doing that at the time. So what I want to do in this talk is literally just pick out 4 aspects of complexity that people are aware of, and which actually might relate to the sort of data that we see around us all the time, and specifically to the data that we see relating to coronavirus. The 4 aspects I'm going to look at are things to do with what's called a data deluge. Again, that's a quote from a famous physicist called Albert Laszlo Barabási. I'll look at the intrinsic properties of complexity that occur in things like sand piles. And then I'll look at some complexity associated with making observations when all around you seems to be changing. And then finally, I'll look at the complexity associated with trying to make decisions when everything is uncertain, which is the sort of thing that we see on the television every day of the week now. So hopefully those things will come together to give you a feeling for complexity, and hopefully it can make you feel much more secure, even though you realize that we all possibly know less than people seem to imagine that they do. So let's move on. When did you first realize that there was a pandemic? When did you first hear about it? Well, as coincidence will go, I don't know whether you realize this, but on the 11th of March 2020, the WHO said that the world is in the middle of a pandemic. It was exactly a year ago today that we actually entered the pandemic. That's a coincidence. I didn't arrange that. It's a coincidence. But actually, that's not the first time I'd heard about the pandemic, and many people who work in this area. And I've shown you here a page or a table from the 2012 edition of the National Risk Register of Civil Emergencies. That's a UK government document issued by the Cabinet Office. It's issued about every 2 years. There's a current one, was issued last November. And you can see in the top right-hand corner, it says pandemic influenza. Now, although it says pandemic influenza, I don't think anybody was actually specifically thinking about influenza at the time. What they meant was a pandemic communicable disease. And it's always been the case when people have thought about emergencies that actually everything else should be measured against that. And actually, that's possibly what we're currently doing. Where pandemic influenza, and in our case, a coronavirus pandemic, is the yardstick that people tend to use. In fact, this diagram is quite interesting. If you actually look at the bottom, it gives some kind of indicative timescale, and it says that pandemic influenza will occur somewhere between 1 in every 20 years and 1 in every 2 years. Well, 1 in every 10 years is about the middle. This was 2012, so actually that's not far from being wrong. But what you shouldn't do is think that actually we've got to wait 10 years for the next one. The next one could come along much quicker than that. That's a rate at which these things are likely to arise rather than a prediction of when they will arise. But it's really interesting to see that this yardstick, if you like, of emergency has been around for quite a long time. In fact, the first efforts at this were produced by the Department of Homeland Security in the United States. This one in 2012 was put forward by the chief scientist at the time, which was a man called Sir John Beddington. He's become Sir Patrick Vallance these days, but in the UK. That thinking about emergency and what are usually called low frequency, high impact events has been going on for a while, and but was always wrapped up in what is termed preparedness. That's a word that comes from the Department of Homeland Security, preparedness, and actually never really achieved much focus. Okay, although it's, I say, people who work in this area and certainly government scientists have known about this risk register for a long time. Now, obviously, in 2020, there was some focus around this coronavirus disease, and the World Health Organization has been really helpful in trying to achieve that focus. And they, not quite a year ago, but close to a year ago, they put together this webpage where you can actually go and look at all the science related to coronavirus disease. This thing allows you to search and filter and all kinds of things like that. It's well structured, well organized, and connects all these databases together, the obvious ones like Medline and the bioRxiv, but also things from publishers like Elsevier and so on. Last time I looked, there are about 250,000 scientific publications in this database. 250,000 science publications. They've all appeared within a year. Now that's amazing. 250,000 science publications in a year, 1,000 a day on one subject. That's staggering. But they are there, and this page organizes them pretty well. You can see that about 100,000 of them appear in Medline and so on. You can search these things by the subject matter. Most of them are to do with infections, and a lot on viral pneumonia, which is an outcome of coronavirus and so on. Lots of different, I've abbreviated these lists. They go on a long way down below the ones I'm showing you. But you can see that there's a huge amount of organization and filtering that goes on, searchability and so on. It really is quite a well-structured set of data. The obvious journals, the British Medical Journal, Nature, the Lancet, Science, all contribute data. In fact, you realize there's 250,000 publications in this database, and the biggest number of publications is in the BMJ of about 2,000. It makes you realize how many different places you would have to look at in order to try and find all this if the WHO hadn't done this organization for us. That's a fantastic piece of effort. I pointed out to Evelina yesterday, actually, I thought if I was going to show this, I should at least show one of the actual publications. So I put this slide together on Tuesday and chose the top publication on the list, the last one that had been entered of the 250,000. Okay, and this was it. And that, again, is another amazing coincidence. Remarks on COVID-19 pandemic in Poland. Now, I don't know what, that was an astonishing coincidence. I can't pronounce what comes underneath there, but clearly that was the last one. Obviously, since then, lots of others have been added, and I'm afraid it's been replaced by this one. That was when I looked the last time in the more than 250,000 now papers. It's about pandemic in the classroom and so on. But what you'll see here is the massive amount of information. But the amazing thing is, that's not what I would call complexity. And it's not what most people would call complexity. Okay, it's structured, it's well organized. And actually, one of the things it does, it allows some element of appreciation of the content of these things without actually reading them, because you can actually use the fact that it appears in this database, its journal and so on, as some measure of trust in its source to give some trust in its content. We can actually connect in that way with this organized set of data. And that's quite useful. And it means that actually, although nobody can read 250,000 papers, there are programs that read these papers, I guarantee you, and they do read all of them. But it isn't what I would call complexity. In contrast, there is a huge complexity in other information about coronavirus. The amount of information that we all get in things like social media completely swamps that amount of information from the WHO. It's enormous compared to that. That information is often called user-centric or always on or networked information. And one of the things that happens is that the sources of those pieces of information that you see on Twitter or in Facebook or that you get from talk radio or from 24-hour TV or those really irritating push notifications that you get on your telephone that tell you how important somebody else thinks something is and so on. All of that stuff is appearing all the time, and it's very difficult then to connect the information with the actual content. We're much more able to connect the information with its users, the people who sent it us, people who like it, who share it, who put thumbs up on it and so on, people who tell us about it on Facebook and things like that. It's much more important about that information than actually what's in it. And that's why it's usually called user-centric information. And it is completely powerful now in many areas of activity for humans and completely outweighs what seems like a lot of information on the WHO website. Normally we would use this structure as a proxy for trust in content, and we can't do that for user-centric information. And something else takes over. What takes over is our internal biases. We all have lots of biases in the way we think. They're usually called cognitive biases. They include things like availability bias, confirmation bias, halo bias. Halo bias is when somebody who you like says something, and therefore you believe what they say because you like them rather than actually you've understood their content. That's called a halo bias. Confirmation bias is that we have so much information coming at us through Twitter, we just read the bits that we believed in the first place. That's just confirmation. So if you go to Wikipedia and look up cognitive bias, you'll find a list of at least 200 different cognitive biases. We're all subject to them all the time. It's impossible to remove them. But actually knowing that they're there and being aware of them is actually quite a good thing to do. And what it means is that everyone sees a completely different pandemic. Our pandemic, the one that we see, the one that we actually hear about, is our own. It's not the one that everybody else thinks, and it's not really the one that somebody who worked hard on the WHO database would distill for us. It's our own epidemic, and that is our first example of how complexity has got into our lives in terms of coronavirus. So that's the first one. So let's move on to another one. You'd think that cases, if just looking at cases is what the pandemic is about, but actually observing illness in the community is actually in real time, is really challenging. And actually it's difficult for almost any disease, never mind one that's communicable like coronavirus. All kinds of surveillance systems exist, active ones and passive ones. Active ones are when you actually go out and look for cases of illness. Passive ones are when people come to you when they're ill and so on, and report, self-report. All of those things fit together. It's very difficult because we've got to define what our particular kind of illness is, a case definition. There are no really good case definitions for coronavirus because it looks so much like flu in the first instance. And when Public Health England do something called syndromic surveillance, where they try and watch for illness, they have a category called influenza-like illness, ILI, the biggest category of things that they spot in syndromic surveillance. And actually coronavirus initially fits in there. Nowadays, we can actually get a PCR test, which is pretty good at identifying a positive. And so in principle, we can count cases, but we still have to be aware that actually the rate at which we find cases is not just about being able to identify them. But then you've got to say, well, how much data do we need? And that's one of these ball of string questions. How long's a piece of string? Actually, you can collect as much data as you like, and you still might not have the perfect answer. We have to live with uncertainty. The statisticians define something called the power, the statistical power. And strictly, it's the chance of detecting an effect if it exists. It's 1 minus the probability of a type 2 error is a technical jargon. But imagine that there is some kind of effect in the population. There is some kind of illness that affects a fraction of us. How much data do we need to collect to see that fraction and not include in that fraction the 0 in terms of its confidence limits? Well, statisticians have known about how to do that for quite a long while. And they do these things called power calculations. And I've done the simple power calculation here for severe coronavirus. So imagine that there was a disease and it's approximately 1% in the population, 1,000 per 100,000 people. Epidemiologists we're talking in terms of numbers per 100,000 people, which is a really weird unit, but it's so that things don't become too small and they don't have to communicate really small numbers. Although it can be as confusing as using the small numbers in the first place, I find. But anyway, 1%, let's say we were happy if it's between 0.5%. We measure something and we're confident that it's between 0.5% and 1.5%. So that's a 95% confidence that's got a precision of 0.5%. Well, that's pretty loose definition of what coronavirus is. But to do that, we would need about 1,600 measurements. 1,600 PCR tests would be required. That's quite difficult to do, especially if once the percentage goes down, we need a lot more data. And if we want our confidence to go up, we need a lot more data. If you want to detect 100 per 100,000 instead of 1,000 per 100,000, and we want to have the same sort of precision, 50% precision, we're getting up into hundreds of thousands of data. It's really difficult to do. There are some sophisticated ways to increase the efficiency of the sampling and so on like that, but notwithstanding, that's how difficult the problem is. But again, what I want to tell you and what I want to emphasize here is actually that's not what most people would count as a source of complexity. It's difficult and we get uncertainty involved, but it's not a source of complexity. So what is a source of complexity in terms of counting cases? Well, it comes down to things like incidence or prevalence. You'll see both of these things are used almost interchangeably. Incidence and prevalence are used almost interchangeably. This Public Health England document here, I mean, that tells you 4,712 cases of new positive cases. That's an incidence. Incidence is usually the difference between two prevalence values. Prevalence is a proportion of a population. If you want to look at, I mean, I said I wouldn't name any data sources, but if you wanted to look up a good prevalence study, I would recommend something called the REACT study. It's from Imperial College. REACT is an acronym. It means real-time assessment of community transition or something like that. They present really good data sets and really accessible data sets in regular documents. I would recommend that. But the incidence actually turns out to be a difference in prevalence values divided by time. And that tells us something really important. Once we have to divide by time, it tells us actually the situation we're thinking about is really dynamic. And modeling tries to build a picture of that dynamics. Okay? That's what the modeling does. All the models that you hear people talk about on the television are doing exactly this. Okay? They're trying to predict that dynamics, build into the dynamics of how we count cases. Okay? Now, the infected people, the prevalence, the fraction in the population who are infected, the prevalence, are usually termed I. Those with a disease are called infected, and they're called I. And if you think about the population, that leaves two other kinds of people. If they're not infected, then they're susceptible to infection, and we call them S, or they've actually recovered from the infection and usually are considered immune, and they're called R. And so what we need to do is look at the dynamics of these three things, the susceptibles, the infected, and the recovered. And that's called an SIR model. And it's iconic in terms of mathematical modeling. SIR modeling, which was first ever considered in around about 1925 by some mathematical modelers, and several at the same time really invented the modeling. But that SIR type modeling, fundamental to trying to understand disease. And even the models that we use today, the sophisticated ones that produce all the decisions are based solely on that SIR modeling. If you think about it, the incidence, the rate at which new infected cases occur, has to be a product of the number of infected cases there are now and the number of susceptible people there are now. Because if either of them's naught, if there are no susceptibles or there are no infecteds, there won't be any new infected cases. So we know immediately that if we're going to build these things into a set of equations, and then the equations are on the next slide, so don't worry too much if you see them and are a bit shocked. If you're going to build these things to equations, clearly the rate of change of the infecteds will depend on the product of the number of infecteds and the number of susceptibles, and it does in an SIR model. The SIR model is a very simple model and easily solved in an Excel spreadsheet. So that's the essence of the modeling. And I'm not going to tell you the details of the modeling or anything like that. So now, the first thing I want to tell you about this picture. This is a fantastic picture. This picture, which you can see, so some fantastic sand dunes. Okay, brilliant sand dunes with ripples on them. In a desert. And actually, it's not any old desert. This desert actually is on the surface of Mars. This is a picture taken by the Curiosity rover. That's not the current one that people are talking about in the news. It was one that was sent up to Mars in about 2011. It's been there for about 10 years and it's still going. The last time I saw the webpage, it was in something called the Gale Crater. It's a little buggy thing and it goes around taking these fantastic photographs. You can download this exact photograph from the NASA website in unbelievable resolution, to the extent that you can't get the full appreciation of how beautiful those sand dunes are on this web page. But if you download it, you can blow this picture up to about 1 meter across and it still looks in unbelievable detail. Those sand dunes like that look absolutely fantastic. Now, to get this picture, clearly they had to put the buggy in a space rocket, fire the space rocket, understand all the laws of motion to get it out of the atmosphere and then across to Mars, stop it when it gets near to Mars, slow it down, get it down to the surface, take off all the packaging, fire up the camera and set it going. Quite a difficult thing to do, but that's not a source of complexity either. I'm telling you that even though that's been done by NASA, it's not a source of complexity. They don't consider it complex, although most of us would. Actually, the formation of the sand dunes easily is a complex thing. I told you I worked on sand pile automata. It's because of things like sand dunes. All of those grains in that massive field of sand blown by the wind managed to organize themselves into those lovely ripples with a particular length scale and sub ripples on the ripples into this fantastic pattern, which actually occurs in many places for wind-blown sand. That is organization out of disorder. It's a pattern formation phenomenon, and it's a well-known symptom of complexity. And if you look at those equations in the top, I'm not going to tell you about solving them or anything like that. As well as you can see that the rate of change of the number of infectors is proportional to the number of infectors and the number of susceptibles. There are 4 parameters in there. One's the rate at which people die and one's the rate at which people are born. So they're pretty easy to find out. One's the rate at which infections die out. So if you keep an infection, how long do you keep it? And the other one is, what is the rate at which individuals make contact with each other? That's really complicated. Only 4 parameters in there, and actually most of the time we take the ratio of 2 of them to get this parameter called R, which you've seen in the news all the time, but it simply is the ratio of these 2 things, the contact rate and the time it takes for an infection to die out in a person. And that determines the whole dynamics. And what I'm telling you is the answers you get when you solve those equations include all these fantastic patterns of complexity that correspond to waves in sand. That's an amazing source of complexity from something that's relatively simple. These disease models allow us to measure things like the rate of contact of people and the rate at which the disease finds out, to try and understand the rate at which the disease spreads through the population. That's an amazing way to cope with complexity. I solved those equations in an Excel spreadsheet earlier this week, and you can see one of the solutions for the set of parameters that I chose are these decaying oscillations. That's probably what we're experiencing in the UK at the moment. We started with a big oscillation, we had another big oscillation, but gradually the oscillations are dying out. The red line here represents the number of infected, so the number of cases, and you see it has an oscillate, a big peak, and then it goes down into a dip and comes up again slightly. And what I think if I was doing this to model the real data, I'd have to try and make the size of the second peak bigger than it is in this. But you can see what I mean. By changing those parameters, we can get really complex pattern forming behavior. And actually, those patterns reflect the myriad of possibilities in terms of human behaviors and behaviors of the virus, the fact that it can mutate, and the fact that people can go to pubs or not go to pubs, and so on. It's all captured in those things. The people who solve these things for a living and work heavily overnight in London School of Hygiene and in Imperial College to do these things, they have far more sophisticated sets of equations because they separate the susceptibles into old age susceptibles and young age susceptibles, and they write down the parameter of context by those people who go to pubs and those people who don't, and those people who meet other people at schools and so on. But the limits on computation are not restrictive at the moment. The limits on understanding the complexity are. So you can see how this is our intrinsic complexity. It's something that's actually another source of complexity that's inherent in understanding disease. And I put this quote here because it's always good to have a 13th century quote in a talk, I always think. So I've got a 13th century quote here. But actually, I would never have been clever enough to find a 13th century quote from Alfonso the Wise, King of Castile. But actually, there's a famous book on mathematical biology written by a man called Jim Murray, the Bible when it comes to mathematical biology, which includes lots of things about SIR models, but also why you get stripes on tigers and why snail shells have got spirals and all kinds of fantastically interesting things like that. And he said, Alfonso the Wise in the 13th century, he said, if the Lord Almighty had consulted me before embarking on creation, I should have recommended something simpler. Well, I think that sums up how complex nature can be to me. And he was doing that in the 13th century, before he read a textbook, I guess. And I think that sums up the intrinsic complexity there is in nature and why we all find it so difficult to understand something that is apparently so simple as a pandemic. So let's move on. Once we've established that we can try and follow cases, we need to try and interpret what cases are telling us. And the way that people do that is actually to look at groups of cases and see if there's anything special about the people who become ill. That's what people do. That's what statisticians do, epidemiologists do. Those things are usually called factors. And understanding those groups of people is a gateway to how we actually try and fight the disease. We fight disease by trying to stop it, obviously, but also by making it less severe or concentrating on people who are particularly vulnerable and so on. What are those factors, the lifestyles, the health conditions that are important? We can do it simply by looking at collecting a bunch of people who are cases, people who are ill, and asking them questions to see if there's anything special about them. Better than that, we can try and compare them to a separate group of people who we call controls, people who aren't ill but are largely the same as the people who became ill. Is there something different about the two cases? That's a case control study. And we try and do that. And in that way, we can associate certain things, particular BMIs, for instance, with severe illness. It's really important to appreciate here that association which we can get is not the equivalent of causation. It's not your BMI that causes you to be ill, but clearly it is associated with illness. You can see that all the studies in the WHO database of the type of study, the one that is most common, is to try and find out what the risk factors are. There are lots of other kinds of studies, but the one that is most common is people are looking for risk factors. Now, I can't believe that there are 20,000 different risk factors, so these things do duplicate. The people who try to find them are well-intentioned, they're trying their best, but they're probably duplicating each other's work, and that probably means that somewhere down this list, there's probably people who are doing things called systematic reviews to try and put risk factor work together and so on. But you can see that we have a fundamental problem here, is that we can find association, but not causation. When I used to teach people like Evelina, I used to try and explain this process by telling people that of all the people in a year, in a given year, of all the people who are actually attacked by a shark, killed or injured or whatever by a shark, almost half of them have recently eaten ice cream. But no one would actually say eating ice cream causes you to be attacked by a shark. It's clearly an association which is there, and most people could explain away, but it's not something that anyone would say was causation. And that's a really important thing. It's easy to get in less dramatic situations than being attacked by a shark. It's easy to be confused association with causation. It's something that adds to complexity. And the reason is because of this. If, let's say, we were interested in this question, does wearing a mask decrease disease? We might draw a line from mask to disease with an arrow on it saying that mask causes decrease in disease. But our problem is that actually, what if being a smoker also affected wearing a mask and disease? Could it be that people who are smokers get less disease anyway, and people who are smokers wear a mask less often? What of those things are related? Because then we might see this association between mask and reduced disease, but actually not know that it's not a causal association, but it's a third thing, a confounding variable that is causing this relationship. And that's a massive source of complexity. It causes us real problems, because that list I've got there of possible things that might link mask wearing and decreased disease, age, sex, smoker, your BMI, previous underlying medical conditions, and a whole other things. That list goes on for a long way. No, it's not 20,000 long, but it's not far off, most of which we don't actually know about and we can't even imagine. And so anything that we can do to try and eliminate those things always leaves us with some doubt. People do try and eliminate particular ones. So for instance, age, you could try and eliminate age from this complex situation by actually looking at the relationship between mask and disease for particular groups of ages. People between 65 and 70, people between 60 and 65. And then looking at the relationship between mask and disease, and then reconstructing the population in terms of its age range from those results between particular ages. That's called adjusting for age. We can do it for several variables at each time, but we always have that nagging doubt that there's something we've missed, that lurking variable that might actually be important in understanding this relationship. And that itself is a cause for significant complexity. In fact, there are some causal questions that cannot even be answered by those traditional. Perhaps go back, I mean, in therapeutical situations, what it's possible to do is randomize over all of those possible confounding variables. And you get this gold standard thing called a randomized controlled trial, which is used throughout medicine and actually works very well to randomize over all the possible confounding variables to give us a possible answer. It's that sort of approach that is used in terms of understanding the efficacy of vaccines, and so that's not subject to this confounding problem, and that's really important. But you know, ask yourself, what placebo would you use to test somebody for wearing a mask? That's not easy to think about. What is the placebo for wearing a mask? There are some causal questions that actually can't be answered by traditional statistical approaches. They're usually historical type questions, and they're called counterfactuals. Whereas we're all used to thinking about, if A happens, then B will happen. That's a causal way of thinking, and we're all hardwired in our brains to think about that. It's a really important part of evolution that we think about that, because it stops us getting hurt. If this happens, if I walk towards the edge of this building, I could fall off and get hurt. That is a really important part of the way that we think. It's a part of thinking. But actually, it's much more difficult to think about, if A had not occurred in the past, B would not have occurred in the past. It's easy for us to actually transfer that to the opposite causal thing and say, if A had occurred, B would have occurred, or if A occurred, B occurs. So that's a really difficult thing. And it leads to these questions like that you often hear people say, how many deaths would have been prevented if lockdown had started earlier? That's a counterfactual causal question, and there are no simple statistical answers to it. And that's a really, really important part of complexity and the third element of complexity that we're talking about. I'm going to plug this man's book here. I mean, Judea Pearl wrote a book you can get in every airport. Not that people go in airports to buy books anymore. The Book of Why. It's called the New Science of Cause and Effect. I would recommend this book. It's a really good read. It's easy to read. It's not mathematical as such, although he is a really high-level mathematician. I suspect Don Mackenzie is more of a journalist and contributed. But in the absence of these clear causal discoveries, the decision-making surrounding intervention causes all kinds of doubts, and we're subject to them all the time. So that's our third one. Now I'm going to move on to the fourth one, which is about decisions, and we're getting towards the end. So I'm going to bring everybody's going to get a chance here to be involved in this. So get ready. You're going to get asked some questions. You're going to have to think of an answer. So uncertainty surrounds everything in this world. Nothing can be said to be certain except debts and taxes. So that's a former president of the United States, not the one you're thinking of. It was actually referring to the United States Constitution. It's by Benjamin Franklin, and he was saying that people have made a really good job at building the Constitution, but actually you still can't say everything is going to be true. What decisions do is they connect our knowledge to what we do. They convert knowledge into actions, and it's a standard part of policy making. How do you take what you know and make a decision? And clearly what we want to be able to say is we based our decisions on the science. Everybody will have heard that. It's actually really difficult to do. And what I'm going to do is put up a few very simple things to convince you that actually other things come into it, whether you like it or not. Other things come into your rationality when it comes to decision making. So a gamble is the fruit fly of behavioral economics. And that was said by a man called Dan Kahneman. Again, he wrote a really good book called Thinking Fast and Slow. And actually, he explains the world according to a set of decisions, and these are some of them. So look at these two choices you've got. These are things subject to uncertainty, but you get a choice. So you could toss a coin and you would win £100 if it came down head, but you would win nothing if it came down a tail. Alternatively, you could roll a dice, a six-sided dice, and you'd win £240 if it came down a six, and nothing if it came down anything else. So if you've got a choice, which one would you do? Would you choose A or choose B? It's a simple choice. You only get only one thing to choose, but actually there's some uncertainty here because actually you don't know whether it's going to come down heads or tails or whether it's going to roll a six. But everybody make up your mind. Choose one of these things because the answer is going to flash up as to what I think most people would say. There is no right answer and no wrong answer to this, but I think I know what most people would say. So have you made your choice? Here's what I think would happen. I think most people would choose A. Expectation is that you win £50 in A. Half the time it comes down heads, so half the time it comes down tails. So about 1 in every 2 times you'd win £100, and you would earn £50. In B, the same situation applies, and it's 1 in 6. 1 in 6 times you'd win £240, and the rest of the time you'd win nothing. So the average would be about 40. It's called the expectation. If you wanted to maximize your expectation, you would choose A. And most people, I think, would do that. I should add that the history of understanding decision making stretches back a long way, back to Jacob Bernoulli and people like that in the 18th century. Goes through all kinds of famous statisticians, Blaise Pascal and so on, Morgenstern, John von Neumann in the United States, Manhattan Project man, looked at these things. And all of them were interested in decision making, but a lot of it comes back down to gambling and games. And if not gambling and games, the law. But they're the two areas where people look at decisions most, gambling and the law. Closely connected, I think. Anyway, it seems that most people here would choose expectation of their reason for making a decision. But what I want to tell you is actually, I think you probably use other things as well. And so the next question, there's a similar choice on the next slide. You're going to have to make a choice again. If the first choice is the same, toss a coin, you win £100 for a head and nothing for a tail. But the second choice now is to win £40 for certain. Which would you choose now? You've got a different choice now. Okay. Again, there is no right answer here. Half the time you're going to win £100 in choice A, and every time you're going to win £40 in choice B. Which one are you going to do? Well, statistics says that most people would actually choose B here. They would actually go with the certainty. And what that means is that people are actually valuing certainty. People are putting some kind of value on certainty. If you've chosen the B here, you've put a value of at least £40 on, of at least £10 on certainty. Otherwise, you wouldn't have chosen B. That's quite an interesting valuation. And statisticians and behavioural economists have looked at this process in detail and know how to value certainty in lots of different situations. Daniel Kahneman, who's a psychologist, won the Nobel Prize. I also think that's quite a big achievement because actually there is no Nobel Prize in psychology. So to actually win the Nobel Prize in psychology is pretty clever. He actually won it for economics. But decision-making in economics and consumer affairs and so on is a crucial part of things. And actually factoring in things like certainty is really important. Other things get factored in as well that are less than objective. Things like dread and fear are factored into some decision making. And so I'm going to leave you with this decision. Imagine you got the chance to intervene in the spread of a disease, and you're given two choices. In one of those choices, the intervention could be that you will save 200 people. That could be a day or a week. But in the other choice, there's a chance that you could save 700 people, but only with a chance of 1 in 3. Now you've got to make that decision. All of a sudden, you're the Prime Minister. Okay. And people say, well, I'm following the science. But following the science, if the science tells you those two things, following the science is not possible. You've got to introduce your value system in order to make a choice between intervention A and intervention B. And the people who make the decisions, the policy makers or the people who implement policy, are having to do that all the time. That's quite a crucial thing that most people miss and think that they can choose just the science. Decision making combines emotional system and a rational system, and that has some inconsistencies. We are all susceptible to particular framing and particular choices, and we are all subject to exaggerated influences from rare impacts and so on. It's a difficult thing to justify particular sets of decisions because it involves some kind of internal value system, and that we all have different internal value systems. Some people value certainty more than others. Some people who are risk-seeking would quite happily have taken that choice of winning £240 for a roll of a dice because they get a thrill out of that seeking risk. Okay? For heaven's sake, some people go hang gliding. I mean, I don't understand that, but people do. That's really important to appreciate when you next see somebody tell you that they've made the decision based on the science. It's not as simple as it sounds. So let's come to a conclusion. Four areas of complexity. Information is dominant user-centric, so everyone sees a different pandemic. That causes complexity. That's a source of complexity. The development of the pandemic is intrinsically complex. It's got all these internal things that allow you to build ripples on sand and so on that none of us can predict just from looking at the equations. That's an intrinsic form of complexity. Even the best mathematicians can't fully get their head around. The actual real situation is often obscured to us by the complexity involved in making the measurements. We can't look back on the pandemic, we can only look forward. And that statistical obscurity, that confounding problem and the counterfactual problem is a massive source of complexity in our ability to gather knowledge that is relevant to what we want to do. And finally, these emotional values that combine rationality with rationality in making decisions so that everybody responds differently. There are 4 sources of complexity, and those 4 things are the origin of these things. Okay? You often hear people say, well, everyone knows that. People who say everyone knows that, actually what they're saying is that my user-centric sphere knows that, but actually that's not a view of what it says in the WHO database. It's actually what each one of us knows because of our user-centric information source. And people often say it's obvious that. Well, actually, that's because people haven't appreciated that it's obvious means that you can't factor in this intrinsic complexity that is all around us for things as sophisticated and as complex as pandemics. You often hear people say, well, if only we had done so-and-so. And that's this counterfactual thing that people like to call on all the time because they think they know the causal link between A and B and can interpret it as a counterfactual link between not A and not B. And that's a really common thing that you see all the time. And you often see people say about other people who make decisions, they just don't understand. And what you're actually saying when you say that is that actually those people have got a different value set to mine. And therefore, the way that they make decisions is not the way that I make decisions. So hopefully, if you know that those sort of, I can't stop anybody from being subject to complexity, but if you know that they're the sort of things that arise from complexity, it can actually make you feel a lot more comfortable in your surroundings in a complex environment than if you're actually unaware that the complexity is causing lots of the hullabaloo and the insecurity that people find. So hopefully, knowing about this complexity makes everyone feel just a slightly bit more comfortable, what in the end is a really situation for all of us. So I'm going to finish now, and that's my finish. So big thanks to Evelina and to everybody at the Polish Society of Engineers for putting up with this, and everybody's enjoyed it. And that's it, really. Thank you.
Thank you very much, Gary. What I can say, I'm really pissed I am not a prime minister because I'm a risk taker, and I think I wouldn't be a prime minister for too long. I would like to open the floor now for questions. I don't think there were any questions coming in a chat, but we are all unmuted now, so I would like to really open a discussion maybe. If anyone would like to ask the question, please feel free. So before maybe someone would like to start, I have one question, Gary. So yeah, you picture all the complexity. How do you think, is it reliable, or how well it actually, does it really make sense, consider complexity, to compare the data from country to country to follow the spread of the behavior of the pandemic, of the virus? Is that reliable, the data, looking at the different graphs comparing country to country?
I don't think the country is significant, but clearly if you live in one place compared to another, you're subject to a different information source. Your user-centric information is different. Those models, the intrinsic complexity that I've described, the model in the UK, which is run in Imperial College and in London School of Hygiene and places like that, has the UK broken down to a really small spatial scale, to sub-postcode units. And they understand the mixing of people in each sub-postcode unit. So a few streets, people, that model includes different, the way that people meet each other and interact with each other at a street level, almost a street level in the UK. That's not true in other places where, I've been to places in the world where actually you might not meet anyone else the next month, never mind the following day. All things like that. Value systems change to do with all kinds of communities. We learn our value systems from our surroundings and from our families and so on. So they change. Everything changes. It's difficult to say that we've got one set of complexity and someone else has got another. Understanding the level of complexity is about putting all those things together. And actually, it's an individual thing. Nobody can actually solve complexity. The only thing you can actually do is try and be aware of it. And being aware that those things occur, I think, is probably pretty universal if you can manage it. But and so, if you live in a very sparsely populated area of the world, you'd be less worried about the people mixing with each other than with a local mutation of the virus and so on. All kinds of things like that you have to get into understanding. And it's difficult for any one person to say that I've got my head around all of this complexity. But everybody, I think, can say, I'm aware that this thing's far more complex than it seems just in a limited view.
Thank you. I think, yeah, everyone should be unmuted now.
I have a question.
Yes, please go ahead, Peter.
Yeah. Hi, Gary. Fantastic talk, as always. You talked about the difficulty of being able to say things like, if only we had done X, then Y. And I kind of understand that. And I was wondering if I think there are any limits on that, if there are some things we can say and some things we can't say, and the implications this has for actually holding our government to account as to the choices they've made.
Yes, well, that's a really good question, because actually that study of counterfactual statistics is actually a current area of research. There are a few research groups around the world that are currently trying to do that. And I would again, if you've not read the Book of Why, I would recommend going it. There's a kind of calculus. I spent a lot of my technical career looking at things called belief networks, and the way that probabilities spread in a network situation. And it's quite a technical thing to do, but it's the sort of thing that a lot of artificial intelligence type things perform in large scale these days, and the way that a lot of what are usually called machine learning exercises take place. In fact, counterfactuals can be done in a similar way, but with not the same technology. One of the things that counterfactual science says is that actually nothing can be, no counterfactuals can be assessed on data alone. You need some knowledge as well as data. And actually trying to understand that is a process that some people go to with a graphical type model. In the same way that trying to understand confounders can be approached using a graphical type model. You don't need to actually adjust for all the possible confounders to try and get a relationship between two variables, a causal relationship. You only need some of them if you understand the way that they are connected. And so I would say, yes, ultimately, I think there will be science that does what you're saying. I think to simply assert that not A would have meant not B, given that we know A meant B, is wrong. But the fact that people will be able to look into not A, meaning not B, may be something that is worked on quite heavily over the next few years. And I think, in areas of social science and behavioral science, I suspect that is a topic of research. The only active group I'm in contact with is one in the United States, and they're quite active in that area. But I think Judea Pearl's group himself still works in that area. So there are possibilities. Fascinating area of research, and because information itself is in a very different state to what it was when belief networks and causal relationships were initially the topic that everybody looked at. I should add, I'm pretty confident people like Google and Amazon know all about this. They're just not going to tell me about it.
Thanks, Gary.
There was one question. So does it mean that the government follow the science?
They do, but not just the science. They, whether we like it or not, the people who make the decisions have their internal value system. And, I guess different people who followed the same science with different value systems, so a different government might have a different decision. In fact, we see that now. I mean, the same science usually applies to Scotland and England, and yet the value system does appear to be slightly different, although possibly I can't even tell whether it's converging or diverging, actually, possibly both. But we shouldn't expect them to be able to devoid themselves of values. You can't expect anyone to just lose all their values. We're all subject to our internal value systems. And although you can, try and weed out people who've got really exceptional values, that's not necessarily the right thing to do. So I don't think. Yep.
Go on, Gary. I was going to just say, can I follow that up with and touch on what you said about AI? because you're absolutely right. There is a lot of work going on in that, and the number of papers that you talked about at the start are certainly being mined by AI routines quite regularly. And I wondered what your view on the role of that going forward in terms of making a valid decision about what to do, as opposed to the biased, if you like, decisions that the government currently make.
Well, I think that is a really fascinating question, and actually it's something that actually I as you say, it's definitely going on. One of the things towards the end of my scientific career, one of the things that became quite relatively straightforward to do was to text mine for causality. So rather than read lots of papers, you get a machine to read papers and look for causal construction in sentences. So you need some kind of natural language programming to be able to do that, something that understands the structure of English, but it can work out certain things. In fact, at the time, we were only looking for one particular kind of causality to do with protein-protein interactions, but I'm sure that can be done for all kinds of other causal effects inside text. And I'm sure that people are doing that all the time. It gets you into all kinds of other kinds of causal effects to do with sentiment and whatever. And that is, a bit of a black art, but I am sure there are organizations in this world who understand all about that and how to not only mine for sentiment, but possibly seed for sentiment too, which actually gets us into a completely different area.
Yeah.
So how would you get people to have a certain kind of sentiment or a certain kind of value? That takes you into an area that I don't really want to get into, but I'm sure there are organizations out there that want to make people feel in particular ways or have particular values, as I'm sure you realize is possible. So I am sure that's an area of active research. I'm not in that research anymore, although when I did work on text mining of causal interactions for protein-protein interactions, it was very beneficial, and I definitely know that it's possible to find interactions between particular proteins that you can then put into some kind of systems biology model that tell you about the metabolism of certain kinds of organisms. So where you would have had to read hundreds of thousands of papers to find those interactions.
No, absolutely, completely agree. In fact, I had a conversation with somebody doing exactly that from the University of Manchester only this week.
Oh yes, I can imagine I might know who that is.
Great talk, Gary.
Do we have more questions? I think
I was just gonna say to Gary, or ask Gary, I was particularly taken with your statement about everybody's perception of the pandemic is very, very different. And the thing it brought to my mind was, these questions that swirl around about human perception, and does everybody see blue as blue? Does everyone perceive red as red, etc., etc.? I mean, it made me wonder if our disparity in perceptive abilities is that wide, across things like
you've got me onto one of my hobby horses now. This is definitely one of my hobby horses, because as you probably know, for a long time I worked in risk assessment and was constantly badgered by people who worked in risk perception. One lady who you may well know, who now works in Newcastle, and I had arguments about what risk perception really was over and over again. And I don't think that word perception, as it applies to risk, and the way that you've used it here, is the same as the word perception as it would be used in terms of user-centric ideas and whatever. My user-centric ideas actually are more about a frame of reference than they are about perception, which I literally take to mean through the senses, without the senses. So you perceive something without actually seeing it or feeling it or smelling it or whatever, and that's a property of humans. That's not true in terms of user-centric information, where we assimilate in a different ways because we're exposed differently. So I would separate those two uses of the word perception, but I've been having this debate for at least 20 years and I don't think I've ever really won it. So it's an ongoing thing for me, but I tend to work in terms of user framing and user centricity rather than perception. I did have a chat once with a lawyer in the United States who told me about something called the Rattlesnake Problem, where it was about the risk to do with a rattlesnake being in your mailbox when you go to collect your mail. If somebody tells you that the rattlesnake is there, you don't go to collect your mail. But you never ever perceive of a rattlesnake in your if you're in the mailbox. There is no perception of the rattlesnake in the mailbox. Only an additional piece of information which changes your frame of reference. So I don't know whether that is true or not, but
Yeah.
perception is a very complicated word. I try never to use it.
Yeah, agreed. Thanks, Gary.
Okay, in the interest of time, I know, Gary, there's many of your colleagues who probably would like to chat to you. I'm very happy to stay longer, but and we can chat. I would just like to close the formal part, the official part of the meeting, by inviting all of you to our next webinar, which will be, okay, can you see my screen actually? No.
Do you want me to stop sharing mine?
Yes, okay. To the next webinar, which will be this Sunday, and it's by Andrew Shidwo. It will be more suited probably for kids. If you've got kids in your family and teenagers, it will be the chemistry show, the magic world of chemistry. It will be colorful, it will be loud, and please do bring your children. I do understand that everyone is tired probably of computers, but this will be different. Zbyszek's passion is to change the way how we teach science. So please do share the information about the next webinar. And with this slide, I would like to finish the formal part. But if there is anyone with a glass of wine and maybe a shot of vodka, please do stay with us. We will be very happy to have a chat, continue the discussion. Thank you. And Gary, thank you very much for a great talk.